Hi everyone, thank you very much for being here watching my e-talk. My name is Francesca Pinna, I'm a postdoc at the Max Planck Institute for Astronomy in Heidelberg, Germany, and I'm going to talk about the interplay of internal and external processes in the buildup of these galaxies. Since this talk has to be relatively short, I cannot show you here all the plots that I have, I cannot discuss all the details of this work, but I will be very happy to discuss them with you and to show you more plots if you write me on the Slack channels or via email. So let's start with the talk. We will talk about fictive star formation histories in AURIGA simulations because we will use them to trace the interplay of internal and external processes. And therefore, let's see what thick disks are. Thick disks are the fainter envelopes of thin disks, and they are usually older, more metal poor, and alpha enhanced than thin disks that are usually metal rich and on average younger. And thick disks are usually studied in giant galaxies because they can easily separate it from the thin disks here, because we can see the vertical structure of these galaxies. So, about the formation of thick and thin disks, both internal and external processes were proposed in the literature. We can have for the thick disk an in situ formation in a Born-Hot scenario with a thick disk which was formed in situ already thick at high redshift. We can also have a pre-existing thinner disk with its stars that were dynamically heated later to form a thicker disk. Or we can have an extragalactic origin with direct accretion of stars from satellites. And in most recent studies, combinations of these processes have been proposed instead of only one of them. For the thin disks, that were formed later on in an extended way in time and allowing for a more extended chemical enrichment. We probably mainly formed them in situ. However, with mergers or in general, external processes playing a key role in providing large quantities of gas to fuel their extended star formation. So thick and thin disks trace different phases of galaxy evolution and together can trace the full buildup of these galaxies. This work is about simulations, but we use simulations to compare to observations and to understand better observations. So from intergraphite observations, we have very few galaxies that allowed for mapping of the stellar populations. And in particular, we have only these 5 galaxies for which we have both metallicity and magnesium over iron mapped. As you probably know, both of them measure chemical evolution, and the combination of them can give us complete information on the chemical evolution. Since, as you probably know, when we form the first generations of stars, we have a very low metallicity because the medium is not enriched yet. And we start to see supernovae type 2 enriching the medium, contributing most of the alpha elements, including magnesium. Therefore, we have a high magnesium over iron abundance. However, if we allow for a slower and longer chemical enrichment, we also see supernovae type 1a with a longer lifetime enriching the medium with the iron peak elements. And therefore, we have a decrease of the magnesium over iron abundance and an increase of metallicity. Having said this, what we can also do from observations, we can plot the star formation histories, for example, in terms of the mass fraction as function of age. So here we have for the thick disks, for example, but they also have the plots for the thin disk, and these are color-coded by metallicity. So each one of the age bins is color-coded by metallicity, but we can also show this for magnesium over iron. So if you're curious about these plots that are not included here, please ask me. So this is a mass fraction of that we find nowadays for each one of the ages and color-coded by metallicity, and therefore these plots can be interpreted as a time evolution, as a chemical evolution from the right to the left. So we see some chemical enrichment, the usual chemical enrichment that we expect for a closed box with the lower values of metallicity on the right and higher values on the left. However, on top of this enrichment, we see these drops and oscillations of metallicities with these blue values, which corresponds to more metal-poor stars. And these stars were interpreted as a contribution from external processes providing more metal-poor gas or stars. Therefore, this is the observational sign of the interplay between internal chemical enrichment and external processes. So now we want to see whether also in simulations we see these drops and oscillations of metallicity and where these contributions come from. And we use AURIGA simulations that are assuming cosmological simulations, including star formation, stellar and their core feedback, and magnetic fields to simulate 30 relatively isolated Milky Way mass spiral galaxies. From this sample, we selected 24 galaxies and we used a similar approach to observations. First of all, projecting all the stellar particles into an edge-on view to allow for a one-to-one comparison with observations of edge-on galaxies. We also used a Voronoi binning to ensure a similar number of particles in each one of the Voronoi bins, and we analyzed a region which is comparable to observations, to what we can find, for example, in MUSE observations. So this is a region of approximately 10, 12 kiloparsecs in radius and 5 kiloparsecs in height. All right, so what we can also do is to perform a geometrical and morphological decomposition into a thin and thick disk in the same way as we do in observations of the John galaxy. So we take vertical surface brightness profiles and we feed them with two different components that are corresponding to the thin and the thick disks. And we find in most galaxies something like this, so a region between the two horizontal lines in the midplane, close to the midplane, which is dominated by the thin disk. And I have to say that the region between the two vertical lines was excluded from the fit because it is dominated by the bar or the bulge. And we find, apart from this region dominated by the thin disk, the rest is dominated by the thick disk. So the region below and above the two horizontal lines. So now that we know which regions are dominated by the thin and the thick disk, we can analyze the stellar populations, the stellar population maps. This is showing the age maps. And in most galaxies, we find a strong difference in age between the thin and the thick disk. And we actually find this young region, which is the thin disk dominated region in blue, with blue colors, and the rest, so the thick disk, is actually dominated by all the stars. We also have metallicity maps with this clearly metal-rich region in the midplane, which is the thin disk dominated region. And in several galaxies, the thick disk show metal-poor values, but in general, more metal-poor, it was more metal-poor than the thin disk. This is magnesium of rare in abundance, and we see the thick disk is usually alpha enhanced, and the values of magnesium of iron are much lower in the thin disk. So the combination of metallicity and magnesium of iron, by the way, they are anticorrelated, and showing that the thin disk allowed for a much more extended chemical enrichment than the thick disk, because the thin disk is younger, metal rich, and less alpha enhanced than the thick disk. All right, I would also like to show you the mass fraction of accreted stars in the thick and the thin disk dominated regions. And in most galaxies, we see that we have much larger fractions of accreted stars in the thick disk region. As in this example, we have up to 60–80% of accreted stars in the Voronoi bins of the thick disk, while only 10–20% or below in the thin disk. So most of accreted stars are concentrated in the thick disk, and this means that the thick disk formation probably occurred mostly in situ in some cases, although we have a significant contribution from accreted stars, up to 65%. So most of the stars were accreted in some of the thick disks. And this also means that the thick disk is a good tracer of external contribution of external processes. Therefore, we focus from now on the thick disk properties, and I will show you here the thick disk star formation histories color-coded by metallicity. But I also have the thin disk star formation histories and both components color-coded by magnesium over iron. So since I don't have time to show them here, please ask me if you're interested in them. Okay, so we have here again the mass fraction that we find in each one of the H bins, similar plots as I show you for observations, and this is color-coded by metallicity. In several galaxies, we see on top of the usual chemical enrichment going from metal poor values on the right, so blue colors, to the orange-red colors, metal-rich values on the left. And on top of this chemical enrichment that is somehow expected, we see some oscillations and drops of metallicity during the star formation history. So going from this orange to yellow-green colors. And we will focus now onto only one of these galaxies, and we will analyze the star formation history of the thick disk. But now, both color-coded according to metallicity in the first row, on magnesium over iron in the second row. And in general, we see, if we focus on the star formation history in the left panels, which is the full thick disk, so all the stars in the thick disk, we have some chemical enrichment from on the right with these metal poor and alpha enhanced stars, and we go towards the left with metal rich and alpha less alpha enhanced or alpha poor stars on the left. So we split the full thick disk, which is showed in the left panels, into the thick disk in situ stars and ex situ stars in the middle and right panels. So we have in the middle panels the in situ stars, and in the right panels the ex situ stars. So we see that the star formation history of the thick disk in the left panels is the combination of the other two columns. If we start with the ex situ stars on the right panels, we see that this was probably a satellite which was accreted around 7 gigayears ago, and this is shown by the chemical enrichment that we have at the end, because this is actually not only the chemical enrichment of the satellite, but this is the final bars of star formation in the last phase of the merger. So this can be used also to date the last merger. And we see we have a strong burst of star formation in this last phase of the merger with these metal-rich values, but also with relatively high magnesium over iron abundances, which are actually higher than the stars at the same ages for the in situ component. So we have this final burst of star formation. We have this final phase of the merger, which is shown by the red arrow in these plots. And this is actually driving this higher peak of star formation in the left panels with these higher values of metallicity that are probably caused by the combination by the mixture of the gas from the host galaxy and the satellite with these more metal-rich values. So this is not purely the gas from the satellite. And for younger ages than 6 gigayears, we don't have the contribution of the accreted stars anymore, and we see that the in situ stars are the ones driving the oscillations of metallicity. And we see in the in situ component these higher peaks of the star formation, which corresponds to metal poor values, and also higher values of magnesium over iron, although this is not very clear, and probably you're not able to see it very clearly. But we have these bursts of star formation which are related to in situ stars formed from gas that was more metal poor and accreted from outside, probably from the satellite or from the intergalactic medium with the gas that was not enriched yet in the past. And also it could be there is probably a contribution from the galactic fountains mixing the gas from the halo of the same galaxy. So yeah, we have seen that the star formation histories of the thick disks are the combination of in situ and ex situ stars. with this interplay of the internal evolution and external processes. And this is all I wanted to say. My take-home message is that the thick disks are mainly formed in situ, but with a significant contribution of ex situ stars, and also in situ stars that were formed with accreted gas. And also that, more importantly, the star formation histories in general result from the interplay of the internal evolution and the external contribution of more pristine gas and more metal-poor stars. Thank you very much for your attention. This is all I wanted to say. And please ask questions on the Slack channels. I will be very happy to discuss my work with you, also via email. Thank you very much, and bye-bye.